NASA sent a spacecraft into the sun before humanity ever got a clear, high-latitude look at the poles of the sun. Parker's solar probe crossed into the corona years ago, flying through the outer atmosphere of the star. Yet the poles remained one of the biggest blind spots in our own solar system. Then another spacecraft finally climbed high enough to look, and the two ends of the star did not give us the simple picture we had spent decades expecting. There is something almost embarrassing about that. In 2019, humanity produced the first image of the black hole in galaxy M87, roughly 55 million light-years away. A clear view of the polar regions of our own star from well outside the usual planetary plane had to wait until 2025. The black hole was unimaginably farther away. The sun is about 8 light minutes from Earth. Distance was never the main problem. The problem was where we were standing. Think of nearly every image of the sun you have ever seen. The orange disk in a science documentary, the white-hot sphere on the evening news during a solar storm, the images from solar observatories showing spots, eruptions, and giant loops of plasma. Almost all of them share the same basic weakness. We have spent centuries looking at the sun, mostly from the side. Earth travels around the sun inside a broad, flat planetary plane. Most of the major planets follow roughly the same arrangement. It is less like bees flying randomly around a lamp, and more like cars moving around the same enormous circular racetrack. Earth sits in that traffic, and every spacecraft launched from Earth begins its trip already moving with Earth. The solar equator is tilted only a little more than 7 degrees relative to the plane of the Earth orbit. That is enough to let us peak slightly north and south during the year. It is nowhere near enough to stand above the star and look straight down at a pole. For hundreds of years, astronomy became incredibly good at studying a three-dimensional star from almost the same general direction. Then, there is an even stranger question. What does north even mean on a ball floating in space? On Earth, the answer feels obvious because your body cheats for you. Gravity gives you down before you ever think about it. The floor is down, the ceiling is up. Drop a coffee mug and Earth settles the argument immediately. Take away the floor, and the argument disappears. Astronauts in orbit can work on what looks like a wall to someone else. There is no universal ceiling hanging over the solar system. There is no cosmic arrow marked up. The North Pole of the Sun is partly a human convention. We choose an orientation so maps, measurements, and equations agree with one another. Nature does not care whether a scientist in California calls one end north or south. But nature does care about rotation, and that is where the harmless labeling exercise turns into real physics. The sun does not spin like Earth. Earth is mostly a solid rotating body. Miami, Chicago, and Alaska do not complete separate days because one part of the planet decided to hurry. The solid Earth carries them around together. The sun cannot do that because the sun is not a solid ball. It is plasma, matter so hot that electrons have been stripped away from many atoms. Different latitudes can rotate at different speeds. Near the solar equator, one rotation takes roughly 25 days. Near the poles, it takes closer to 34. Imagine a soft ball whose middle keeps sliding ahead while the caps lag behind. Now run magnetic field through that moving material. The field gets stretched and twisted. It gets carried along by plasma that refuses to rotate as one rigid piece. This differential rotation is one of the ingredients behind the magnetic complexity of the sun. Over time, the magnetic system is wound up, distorted, rearranged, and rebuilt. Sunspots appear. Active regions form. Powerful eruptions become possible. Over about 11 years, the visible level of solar activity rises and falls. Over roughly 22 years, the magnetic system completes a broader cycle because the magnetic polarity reverses and later returns to its original orientation. So the poles are not boring caps at the ends of a glowing ball. They are deeply involved in the magnetic bookkeeping of the entire star. That should have made them easy targets for spacecraft. Instead, getting above the sun turned out to be brutally difficult. Earth moves around the sun at about 18.5 miles every second. Every spacecraft sitting on a launch pad in Florida or California already owns that sideways speed before the rocket engine lights. Imagine sitting on the outer edge of a spinning playground carousel. Someone tells you to jump directly toward the center. The moment you leave the seat, you do not magically lose the sideways motion you already had. You keep carrying it. Spacecraft do the same thing. Going outward toward Mars, Jupiter, or beyond is difficult. But there are well-understood ways to add energy to an orbit. Climbing far above the planetary plane is a different problem. You have to turn the direction of an enormous existing velocity. That costs a ridiculous amount of energy. So the first spacecraft built to explore the poles of the sun did something that sounds completely backward. It flew away from the sun. Ulysses launched from the cargo bay of Space Shuttle Discovery in October 1990. It was a joint mission of ESA and NASA. The original mission was expected to last about 5 years. Ulysses did not head straight for a solar pole. It went outward toward Jupiter. In February 1992, the spacecraft passed the giant planet and used the gravity of Jupiter to bend its path dramatically out of the normal planetary plane. Jupiter acted like a gigantic gravitational corner in the road. Ulysses came in traveling mostly with the planets and left on an orbit tilted by nearly 80 degrees. That maneuver produced a wonderfully absurd detail. A spacecraft designed to study the sun had to travel so far from the sun that sunlight became a poor way to power it. Near Jupiter, solar panels of the type available for that mission would not have provided enough practical power. So Ulysses studied the sun while running on a nuclear power source. Sometimes the shortest path to understanding the nearest star goes past Jupiter with plutonium in the trunk. Ulysses passed over the southern polar region in 1994. It crossed the northern high latitudes in 1995. It later repeated those journeys during different phases of solar activity. It had no camera designed to give us a normal photograph of the surface below. Ulysses was more like a weather station thrown through space. It measured particles, magnetic fields, cosmic rays, and the solar wind directly where it traveled. And the solar wind immediately became much stranger. The sun is constantly losing matter. It blows electrons and atomic nuclei outward in every direction. This stream is called the solar wind. It fills the space between the planets. Earth is sitting inside it right now. So is every satellite around Earth. So is the moon. Before missions could sample the sun far from the equatorial region, our natural view was heavily biased by where Earth happens to live. Near the broad equatorial region, the solar wind can be relatively slow and messy. Its speed may sit around a few hundred miles per second and change significantly as different solar structures rotate past. At high solar latitudes, during quiet solar conditions, Ulysses found something cleaner and much faster. The wind could approach roughly 450 miles per second and remain remarkably steady. This changed the mental picture. The wind near Earth was not necessarily the normal state of the whole sun. Earth was sitting in one particular neighborhood and mistaking local traffic for the national average. The reason has a lot to do with magnetic geometry. Many magnetic field lines near active solar regions form loops. A field line leaves one area, arcs through the solar atmosphere, and connects back to the sun somewhere else. Picture a dog running on a long leash tied to a post. The dog can move, but the route is still connected to home. Charged particles moving along closed magnetic structures can remain trapped or redirected. Over large polar coronal holes, many field lines are effectively open into interplanetary space. A particle traveling outward along one of those lines has a much easier path away from the star. The door is open. Those dark regions in the corona are called coronal holes. They are not actual holes cut into the sun. They look dark in certain wavelengths because the plasma there is cooler and less dense than surrounding coronal regions. But they are major sources of fast solar wind. Sometimes a coronal hole extends far enough toward lower latitudes that its fast stream sweeps across Earth. Then a process that normally dominates high above the solar equator can suddenly become very personal. The magnetic field around Earth gets disturbed. Auroras can spread farther south than usual. Satellites can experience changes in drag and charging. Radio systems can be affected. Navigation can become less reliable. Because the sun rotates, the same long-lived coronal hole can face Earth again roughly one solar rotation later. Space weather forecasters sometimes see the same pattern come back again and again, like a problem neighbor who visits on a schedule. This alone made the poles interesting. Then Ulysses found something more uncomfortable. The north and south did not match perfectly. At high latitudes, the wind from the north could run roughly 10 to 16 miles per second faster than the corresponding southern flow during some measurements. That difference is small compared with the total speed of the wind, but it was persistent enough to matter. Other quantities leaned the other way. Work led by Robert Ebert found that during parts of the Ulysses mission, the southern high-latitude wind could be denser and carry a greater mass flow and energy flow than the northern wind. So one side could be faster, the other could be heavier. Then cosmic rays joined the argument. Cosmic rays are extremely energetic particles that arrive from outside the immediate solar environment, many from sources across the galaxy. The magnetic field and solar wind help control how easily those particles penetrate deep into the solar system. Ulysses found substantial north-south differences in cosmic ray intensity at the same solar latitudes, with differences that in some cases reached tens of %. Now the problem was no longer one odd measurement. The north could have faster wind, the south could have denser flow. Galactic particles could penetrate the two sides differently. One star was beginning to behave like two neighborhoods connected to the same furnace. Solar physicists had possible explanations. One involves the enormous boundary called the heliospheric current sheet. The name sounds like something designed to make ordinary people leave the room. The idea is simpler than the name. The magnetic field of the Sun has regions of opposite polarity. Between large regions pointing in different magnetic directions lies a vast, warped boundary. That boundary stretches outward through the solar system with the solar wind. It is not a flat sheet. The magnetic axis of the Sun does not line up perfectly with the rotation axis. As the Sun rotates, the current sheet becomes a giant rippling surface. The standard comparison is the skirt of a spinning ballerina. Earth repeatedly moves through this warped magnetic boundary as the Sun turns. If the shape of that sheet is uneven, or if one solar hemisphere is more active than the other, a spacecraft can measure apparent north-south differences, even if part of the difference comes from geometry rather than from some permanent property of the star. That is one reason the mystery is still alive. Are the two sides intrinsically different? Are they temporarily different because the solar cycle is never perfectly synchronized north to south? Or have we spent decades sampling a complicated three-dimensional system along awkward paths and then asking why the numbers refuse to line up? Ulysses could not settle it. In fact, Ulysses created another problem. When scientists compared the high-latitude solar wind from the first polar passages with measurements roughly 13 years later, the Sun itself seemed to have changed. The fast wind was still fast, but it carried less. Around the later minimum, the high-latitude solar wind was roughly 1/5 less dense than during the earlier minimum and somewhat cooler. The interplanetary magnetic field had weakened by more than a third. Electron fluxes had also dropped substantially. The speed remained close to the old value. Imagine turning on a garden hose and watching water leave at nearly the same speed, except there is less water behind it and less pressure in the system. The Sun was still blowing. It was simply blowing a thinner wind. By 2008, measurements showed an unusually weak solar wind compared with much of the previous space-age record. That was another warning against treating the Sun like a constant machine. Humans like the Sun to be reliable. It rises. It sets. The calendar works. Florida remains warm. Solar panels generate electricity. The star feels like the definition of something that does not change on human timescales. Then one spacecraft spends less than 2 decades sampling it from a new angle and watches major properties shift. Ulysses also found that the magnetic field near the polar regions was weaker than some earlier expectations. It detected far more interstellar dust entering the solar system than some estimates before the mission had suggested. Depending on which pre-flight estimate is used, the mismatch could be enormous, reaching roughly an order of magnitude or more. This did not mean astronomy had been careless. It meant we had been trying to estimate a three-dimensional environment while living inside a flat sampling lane. Every new angle had the potential to embarrass an old number. 2 much older spacecraft added another piece of evidence. Voyager 1 and Voyager 2 were traveling toward very different parts of the outer solar system. Voyager 1 eventually escaped through a northern direction. Voyager 2 escaped through a southern direction. Both spacecraft reached the region where the solar wind, after traveling billions of miles, finally runs into the material between stars. That interstellar material is unbelievably thin by Earth standards. Near our solar neighborhood, a representative density may be around a fraction of an atom per cubic centimeter. A sugar cube-sized volume of ordinary air contains an absurd number of molecules. The same size volume in local interstellar space may contain much less than 1 atom on average. Calling that empty feels reasonable. Physics disagrees. Even that tiny amount of matter becomes important when the solar wind has been expanding into it for billions of miles. The Sun creates a giant cavity in that environment called the heliosphere. For decades, illustrations made this region look temptingly neat. Then the Voyagers actually touched its outer boundaries. Voyager 1 crossed the termination shock, where the solar wind slows dramatically, at about 94 times the distance from Earth to the Sun. Voyager 2 crossed the same type of boundary much closer in, at about 83.5 times that distance. That is a difference of more than 1 billion miles. The outer heliopause also appeared at different distances along the two trajectories. Voyager 1 crossed into interstellar space in August 2012 at roughly 121.5 times the Earth-Sun distance. Voyager 2 made its crossing in November 2018 at roughly 119 times the Earth-Sun distance. The outer difference was smaller than the termination shock difference, but the crossing itself behaved differently too. Voyager 1 spent weeks moving through a complicated transition with repeated changes in particle populations. Voyager 2 experienced a much sharper crossing. Scientists, including Leonard Berlanga, found differences in magnetic structure near the southern boundary, including a stronger interstellar magnetic field and a compressed magnetic barrier near the edge. The heliosphere was not a perfect soap bubble. It was being pushed, distorted, and shaped by the interaction between the solar wind and the local interstellar environment. The north-south differences seen closer to the Sun were now connected to a larger fact. Even the enormous region controlled by the Sun is not perfectly symmetric. There is an important caution here. The Voyagers did not travel through mirror image paths. The solar cycle was in different phases when the two spacecraft reached their boundaries. The external interstellar magnetic field also presses on the heliosphere from a particular direction. Modern models no longer describe the heliosphere as a simple north-south squashed ball. So the Voyager measurements do not prove that one solar pole permanently builds a larger side than the other. They prove something more useful. The real heliosphere is complicated enough that the view from one direction cannot stand in for the whole system. That was becoming a theme. Ulysses had measured the poles without photographing them. Voyager had felt the distant consequences without seeing the source directly. What everyone still wanted was a better view. That job eventually fell to Solar Orbiter. Solar Orbiter is a joint ESA and NASA mission. It launched from Cape Canaveral in Florida in February 2020 aboard an Atlas V rocket. Its strategy was almost the opposite of Parker's Solar Probe. Parker is the daredevil. It dives astonishingly close to the Sun. It has flown through the corona and passed within only a few million miles of the visible surface. Solar Orbiter does not win the contest for closest approach. Its trick is angle. Sometimes the best way to understand something is not to get closer. It is to move sideways. Solar Orbiter repeatedly used Venus to change the tilt of its orbit. Each encounter with Venus nudged the spacecraft farther out of the usual planetary plane. The process took years. This is what makes the comparison with Parker so strange. NASA had already sent Parker into the outer atmosphere of the Sun before humanity had obtained a clear, high-latitude view of the polar regions. We reached the star before we properly looked over the top of it. Solar Orbiter had produced useful views of polar regions before 2025, including images released in 2022. What changed in 2025 was the geometry. The spacecraft reached an orbital inclination of about 17 degrees relative to the solar equator. That still does not sound like standing directly above the pole. It was enough to change the game. In March 2025, Solar Orbiter observed the southern polar region from a high-latitude perspective, unlike anything available before. Its instruments could finally reduce the extreme sideways distortion that had plagued polar measurements for generations, and the timing was almost comically perfect. The Sun was near the period when its global magnetic field was changing polarity. The polar regions were a mess. A normal bar magnet has a wonderfully reassuring personality. One end behaves like one pole. The other end behaves like the opposite pole. Sprinkle iron filings around it and school science becomes tidy. The polar magnetic map of the Sun during reversal is not tidy. Positive and negative magnetic patches appear mixed together. The south polar region observed by Solar Orbiter showed a patchwork of opposing polarity. Later, pole-to-pole magnetic mapping also showed the northern polar region in a similarly complicated state. This was not a surprise that destroyed solar physics. That distinction matters. Models of the solar magnetic cycle already expected the polar fields to become mixed and disordered while the global field reverses. What Solar Orbiter did was let us look at that transition with a much less awful viewing angle. For decades, we had watched the renovation through a narrow gap in the fence. Now someone moved the ladder. Observations from the Japanese Hinode mission and other solar data suggest that the most recent polar reversal developed through 2024, with the southern polar region reaching its new dominant polarity around the fall of that year, and the north following around the same period. That means Solar Orbiter raised its viewpoint just after a major magnetic reorganization. It did not photograph a calm pole. It photographed a workplace after the furniture had been dragged across the room. Another Solar Orbiter instrument added motion to the picture. The instrument, called SPICE, can use the Doppler effect in light emitted by solar plasma. The basic idea is familiar to anyone who has heard an ambulance pass on an American highway. The sound changes as the ambulance approaches and then moves away. Light does something related. The wavelengths shift slightly depending on whether glowing material moves toward or away from the observer. By measuring these shifts in light from ions, such as carbon in a thin transition region of the solar atmosphere, scientists can map motion. That is important at the poles, because old measurements were made at terrible angles. Watching a flow sideways makes speed difficult to measure. Watching closer along the direction of motion is much better. The new polar observations showed complex patterns of material moving outward and material participating in flows back toward lower layers. The polar atmosphere is not a simple exhaust pipe. Some plasma escapes into the solar wind. Other plasma circulates, slows, falls, and gets recycled through magnetic structures. A star is not a furnace with two chimneys. It is a moving magnetic fluid whose atmosphere is constantly leaking, looping, collapsing, and escaping at the same time. That brings us to the reason the poles matter far beyond a photograph. The magnetic field near the poles is one of the best clues we have about the future solar cycle. In 1978, Kenneth Shatton and colleagues proposed a relationship that became known as the polar field precursor. The practical idea is surprisingly simple. Measure the polar magnetic field near solar minimum. A stronger polar field tends to be associated with a stronger next cycle. A weaker polar field tends to be associated with a weaker one. This relationship has worked well enough across several cycles that polar field strength remains one of the most valuable inputs in long-range solar cycle forecasting. The mechanism involves the slow transport of magnetic flux across the surface of the sun. Sunspots usually appear in magnetic pairs. As active regions decay, their magnetic material does not simply vanish. Flows across the solar surface carry part of that magnetic flux toward the poles. Month after month, old polar flux gets canceled. New flux of the opposite sign accumulates. Eventually, the old dominant polarity disappears. The pole reverses. The newly built polar field then becomes part of the magnetic seed from which the next cycle develops. In modern solar dynamo models, that is why the poles can be described as the memory of the sun. They store the leftovers of the current cycle in a form that helps shape the next one. The top and bottom of the star are not the attic. They are part of the archive. Now we have reached the point where the story becomes more useful for people who will never own a solar telescope. A solar cycle is not merely a pretty graph used by astronomers. It changes the environment around Earth. During more active periods, powerful flares and coronal mass ejections become more frequent. A coronal mass ejection is a huge eruption in which the sun throws magnetized plasma into space. If one of those eruptions is aimed toward Earth, and the magnetic orientation is favorable for strong interaction, Earth can experience a severe geomagnetic storm. Then things built by humans begin to care. GPS cares. Satellites care. Power grids care. High-frequency radio cares. Navigation systems care. The people repairing those systems definitely care. The storm of May 2024 provided a very American example. It reached the highest level on the NOAA geomagnetic storm scale. Auroras appeared unusually far south across the United States. At the same time, precision agriculture systems relying on GPS experienced serious problems during planting season. Modern American agriculture is not a farmer steering by a fence post. Large tractors can use satellite navigation to maintain extremely precise rows, repeat tracks, manage seed placement, and guide automated equipment. During the storm, some systems lost enough positioning accuracy to disrupt work. NOAA later cited estimates suggesting potential losses to American agriculture above $500 million. A disturbance born on the sun traveled roughly 93 million miles and ended up confusing farm machinery in the Midwest. That is the kind of connection that turns solar physics from wallpaper into infrastructure. No single solar pole causes a single GPS failure. The relationship is not that simple. The importance of the poles is longer term. They help tell us about the magnetic condition from which future solar activity develops. And right now, that forecast is not as clean as anyone would like. Recent measurements and models have raised questions about the strength of the polar magnetic field, particularly in the north. One study released near the end of 2025 projected an unusually weak polar field through part of 2026. That naturally suggested the possibility of a weaker future cycle. Then another study released in July 2026 looked at the evolution differently. Its authors argued that the weak northern field may be temporary. Under their model, flux transported toward the pole could strengthen the field again before the next minimum. The predicted polar field could even end up stronger than at the previous minimum. Both ideas cannot be treated as established fact. The newer work is still part of an active scientific argument. That is exactly why the subject matters. We finally gained a better view of the poles, at the same time that the poles stopped giving a simple answer about what comes next. The instruments improved. The uncertainty survived. Science does this more often than documentaries admit. Better data does not always produce a clean answer immediately. Sometimes better data kills the clean answer you thought you had. There is another irony. For most of human history, people treated the sun as the most obvious object in the sky. You do not need a telescope to know it is there. You cannot avoid it. It grows food. It burns skin. It heats asphalt in Arizona until touching a car door feels like poor planning. And yet, some of the basic geometry of how the sun behaves outside the planetary plane remained poorly sampled until the space age was already old. This gap has attracted alternative explanations. One of the best known is the electric sun idea, associated with American engineer Ralph Jurgens. In the 1970s, Jurgens, influenced by the catastrophist ideas of Immanuel Velikovsky, argued that the sun should not be understood primarily as a self-contained thermonuclear object. He proposed that the sun was part of a vast electrical environment and behaved more like an electrode in a cosmic discharge. In that picture, some properties of the solar wind and plasma structures are interpreted as electrical current phenomena operating on a solar system scale. Later writers, including Wallace Thornhill and Donald Scott, continued versions of this approach. Supporters often point to filamentary plasma, electrical behavior in laboratory discharges, auroras, and the fact that space is filled with charged particles. Projects such as Sapphire have also been presented by supporters as attempts to investigate plasma behavior relevant to these ideas. The scientific status is clear. The electric sun model is not accepted as a viable replacement for the standard solar model. One major problem is energy. The sun produces an enormous, stable energy output. Any external electrical power system capable of supplying that energy would need a measurable current and an equally enormous external power source. The required system has never been observed. There is also the neutrino problem. Nuclear fusion in the core produces neutrinos. These tiny particles pass through ordinary matter so easily that vast numbers escape directly from the interior of the sun. Detectors on Earth measure solar neutrinos. The measured neutrino flux and its energy spectrum agree with nuclear reactions expected inside the sun. Helioseismology provides another independent line of evidence. Waves moving through the sun let scientists infer conditions inside the star in much the same way that earthquake waves reveal the interior of Earth. Those measurements also match a hot fusion-powered interior far better than an externally powered electrical shell. Science writer Michael Shermer later pointed out that the original Jurgens work was closely tied to attempts to defend Velikovsky-style catastrophism and was not accepted for publication in Nature. Critics, including astrophysicist Tim Thompson and physicist Tom Bridgman, have emphasized the energy budget, neutrinos, and basic plasma physics as major problems for the electric sun model. That does not make the alternative historically uninteresting. It explains why it survives. The sun really is electrical. Space plasma really does carry currents. Magnetic fields and electric fields are inseparable parts of plasma physics. The disagreement is not over whether electricity exists around the sun. It obviously does. The disagreement is over whether an external cosmic electrical circuit powers the star. The evidence says no. Another alternative exists in parts of Russian-language fringe physics. Vladimir Otsukovsky and writers influenced by ether dynamics have proposed models in which an assumed ether flows through or around astronomical bodies. In some versions, the sun is described as drawing ether inward through polar regions and expelling it nearer the equator. That produces an appealing visual explanation for polar differences. Something goes in through the ends and comes out through the middle. The problem is that the required ether has never been detected in the form demanded by the model. Modern relativity, particle physics, solar neutrino measurements, helioseismology, and direct plasma observations work without that mechanism. So this remains a fringe hypothesis without accepted experimental support. Then there is the internet version. Whenever an agency releases a first-of-its-kind image, someone eventually asks whether the real images were withheld. The polar observations were perfect material for that instinct. For years, people heard that the poles were difficult to see. Then spectacular images appeared. The southern views became public before many people understood what had changed in the orbit. Comments appeared asking what was on the unseen side, whether agencies were holding something back, or whether something unusual might be hidden above the sun. There is no credible evidence for a hidden object sitting over either solar pole. The interesting part is why the idea feels plausible to some people. The information gap was real. The conspiracy built inside the gap was not. We genuinely had poor direct views of the poles. We genuinely spent decades inferring their behavior indirectly. That is enough uncertainty to make imagination move in. Reality already provided plenty of mystery without needing a spacecraft parked behind the sun. Ulysses never lived to see the images that finally gave the poles a face. Its ending was almost as strange as its mission. The nuclear power source slowly weakened with age. At launch, it provided roughly 285 watts. Near the end, output had fallen to around 195. That does not sound dramatic until you remember that a spacecraft cannot plug into a wall. Power had to run instruments, communications, heaters, and everything needed to keep the machine alive in deep space. The most dangerous problem became the hydrazine fuel. If the fuel lines became too cold, hydrazine could freeze. If the fuel froze, the spacecraft could no longer control its orientation properly. If the antenna could not stay pointed toward Earth, the mission was effectively over. Engineers came up with a wonderfully practical solution. They fired the thrusters at intervals, not mainly to change the orbit, to warm the plumbing. Ulysses was using its own fuel system like a driver in a freezing parking lot, starting the engine every few hours just to keep the vehicle alive until morning. That trick extended the mission. Eventually, physics collected the bill. On June 30, 2009, controllers sent the final commands. The transmitter was shut down. Ulysses had lasted about 18.5 years instead of the planned 5. It had crossed the high-latitude regions of the sun repeatedly during very different phases of solar activity. It had measured the fast wind. It had exposed north-south asymmetries. It had watched the solar wind weaken. It had measured interstellar dust and cosmic rays. It had even detected roughly 1,800 gamma-ray bursts from distant cosmic events, while doing a job it was never built around. The mission helped produce more than 1,000 scientific papers, and it died without ever showing us a normal photograph of the place it had spent its life exploring. Solar Orbiter inherited that unfinished job. Its orbit will not stop changing at 17 degrees. A Venus flyby in December 2026 is planned to increase the orbital inclination to about 24 degrees. Later maneuvers are expected to push the angle to roughly 33 degrees by 2029. 33 degrees still is not directly over the pole. It is dramatically better than trying to inspect the top of a baseball while keeping your eyes near the height of the stitching around the middle. Every added degree improves the ability to separate true polar structure from the distortion created by our viewing angle. That matters because the central question is still open. Are the North and South permanently different in a meaningful way? Partly. We know the sun can display real hemispheric asymmetries. One hemisphere can lead the other in magnetic activity. Sunspot production can differ north to south. The solar wind can differ. Cosmic ray access can differ. The magnetic reversal does not have to happen at exactly the same moment at both poles. But some differences change with the solar cycle. Some come from temporary active regions. Some come from the shape of the global magnetic field. Some come from where and when a spacecraft samples the system. And some may still represent deeper asymmetries that we have not observed long enough to understand. We have only watched the sun closely for a tiny fraction of its life. The modern space age covers less than a human lifetime. Even the 11-year cycle means a spacecraft can spend 20 years working and witness only a few complete magnetic seasons. That is not much of a sample. Imagine trying to understand the climate of the United States after observing only 3 winters. You would learn a lot. You would also make some spectacular mistakes. That is roughly where solar polar science still lives. We know much more than we did before Ulysses. We also know enough to see the holes in the picture. So what is actually above the sun and below it? Nothing exotic is required. There is no ceiling. There is no floor. There is space filled with thin plasma, magnetic fields, photons, cosmic rays, dust, and the solar wind flowing outward. North and south are names we placed on a geometry. The strange part is not that space above the sun contains something secret. The strange part is that the star behaves differently in those two directions. The north can send a slightly faster high-latitude wind. The south can send a denser one. The magnetic field can reverse on slightly different schedules. The heliosphere built by all of this can be distorted on a scale larger than the orbits of every major planet. And the fields at the poles become part of the memory from which the next solar cycle develops. That memory matters to Earth. It matters to the satellites carrying communications and weather data. It matters to GPS receivers and tractors crossing fields in Iowa. It matters to airlines and radio systems during severe space weather. It matters to power grid operators watching geomagnetic currents. And it matters because our star is not a glowing lamp sitting 93 million miles away. Earth lives inside its atmosphere. The solar wind is that atmosphere stretched across the solar system. The magnetic field of the sun reaches us every second. We have simply lived inside it so long that we stopped noticing. That may be the biggest lesson hidden in the poles. For centuries, we thought the difficulty was distance. It was not. We could photograph a black hole 55 million light-years away. We could send Parker's solar probe through the corona. We could push Voyager into interstellar space. The hard part was moving a camera a little way out of the flat lane where Earth was born. One change of angle was enough to expose magnetic disorder during a reversal. Cleaner views of polar flows, better measurements of the regions that help seed the next cycle, and old questions about why north and south do not behave exactly alike. The sun did not suddenly become stranger in 2025. We finally moved our chair, and for the first time, we could see what had been sitting just above the edge of the table all along.